Our video today is all about the weird and wonderful world of particles. And our main scientist of the day is our only living physicist on our A-level course, and that's a gentleman called Murray Gell-Mann, who was one of the main particle physicists in the 60s, and as you can see, he won the Nobel Prize in 1963. And he was the gentleman who gave the fundamental particles that make up our nuclear particles their name. He called them quarks. And that's what we're going to be exploring today, is what are fundamental particles and where are they found? To introduce this idea, we need to look very closely at the atom, as we've been doing for several videos now. We know that the atom is made up of a nucleus with electrons in various energy levels around that nucleus. The nucleus itself, we know, is made up of protons and neutrons. Various discoveries to establish that for us. And then with deep inelastic scattering, which I've covered in an earlier video, we've discovered that the protons and neutrons themselves are not the end of the story. They are made up of smaller particles that Murray Gell-Mann called quarks. With deep inelastic scattering, when this technique was discovered and used extensively, physicists got very frustrated because of the shower of particles that came out of all of these interactions in these accelerators. Physicists are not used to having lots of things that they have to name and remember the names of, and discovering these more and more and more particles that seemed to be endless. And they named it the particle zoo because they were starting to feel a little bit like biologists, just finding all these different things. But it did settle down after a while, and they discovered that actually patterns were emerging, much to their relief. And that's what we're going to look at today, is what patterns can we see in these particles that are produced. So we start by looking at a family tree of all particles. And that starts with fermions. Now, fermions are what subatomic particles are called. So this is their general name. And we can divide those into two basic groups: the hadrons, which are the particles that are made of quarks, and leptons, which are the other family of particles that are not made of quarks. We'll deal with the leptons first because that's a slightly smaller group. There are two kinds of leptons: electrons and neutrinos. Now, I call them electrons rather than electron because there are different types of them, but they're all sort of fundamentally the same, and they belong in this group of electrons. And the same for neutrinos. There are a few different types, but they're all fundamentally the same. Now, these are fundamental particles. In other words, they have no component parts that we're aware of. So they cannot be broken down. They're not formed of anything else. The hadrons, on the other hand, do have also two groups within them called the baryons and the mesons. Baryons are very familiar to us. Protons and neutrons belong in the baryon family. Mesons tend to be very, very short-lived particles, so it's not something that most people will encounter at any point in their lives. They do exist. They were produced during all of these particle interactions, though, so we need to be aware of their existence. There are lots of different types of both baryons and mesons. You do not need to remember every different type. I'm going to show you them in a second, or some of them. But you do need to know the fundamental properties that they share. So here's our Hadron family in a little more detail. Our baryons are made up of 3 quarks or 3 antiquarks. So you can get antibaryons. A proton is an example of a baryon. You can see it there in this family. There is such thing as an antiproton that is almost exactly the same as a proton, except it's made up of the same quarks, but their anti-version. Neutron is also a baryon. So 3 quarks, 3 antiquarks. You do need to know the quark structure of protons and neutrons. And I will tell you exactly what the quarks are later on, and we will discuss protons and neutrons. There are other kinds of baryons: sigma, delta, omega, lambda, so on, so on, and so on. Again, you don't need to remember the quark structure of anything but the protons and neutrons. You will be told or be able to deduce the quark structure of other things. Now, this seems like gobbledygook to the uninitiated when you start talking about all of these, but actually this is a very simple topic, and if you can grasp this, there are a lot of marks available for people who just are able to deduce what is going on. On the other side of the Hadron family, we have the mesons, and those are made up of a quark and an antiquark. Like I said, very short-lived. You do need to know or recognize some of the more common mesons, pi mesons in particular, are favorites that come up. You need to recognize that if you see a pi symbol, that you're talking about a meson and not a baryon. There are K mesons and eta mesons, there are others, but those are the most common ones. Now, what are we talking about when we talk about these quarks? Well, here are the fundamental particles. We have our leptons that I mentioned before. This is the smallest group and the easiest to understand. We've got small, medium, large. This is the electron family up here at the top. So electrons we're very familiar with. Its antiparticle is a positron. That is the only antiparticle that was given its own name. It was the first one to be discovered. Once they discovered that everything had antiparticles, they gave up giving them specific names because they would just end up with even worse of a situation than you had already. So we have the electron and its antiparticle, the positron. They're exactly the same in mass. They just have the opposite charge. Then we have medium-sized electrons, also known as muons, given the little symbol mu like this. And again, it has its antiparticle, same mass, opposite charge. And then the biggest of the electron family is the tau particle. And again, it has an antiparticle. So over here you can see the rest masses of these. Now you should be able to convert these into kilograms. In my previous video I showed some calculations using megaelectronvolts and gigaelectronvolts per c squared. We will do another example of this down at the end of this video so you can see exactly how to convert these, but that just gives you an idea of mass. It's an equivalent energy amount of mass. So you can see electron is 0.511 megaelectronvolts per c squared, and the tau is the biggest at 1780, so it's significantly bigger. They all have the same charge, or electronic charge, that we're familiar with. The other kind of lepton is the neutrino, down here. These are tiny, tiny, effectively massless particles. And each electron has its own neutrino. So it's like a little companion particle to an electron. So you have an electron neutrino, a muon neutrino, and a tau neutrino, and of course each of those have their antiparticles as well. And when we write neutrinos, I've written them here as a V because that's what the computer can do. It's a V with a little curl in it. The neutrinos are written as electron neutrino, or a bar is put over the top when you mean anti-electron neutrino. Those are our first six, our leptons. The quarks also come in six. Most of our matter, all of our very familiar matter, in fact, consists of up and down quarks. So a proton, for example, is up, up, down. We know it's a baryon, we know it's going to be made of 3 quarks. It is made of 2 ups and a down. And you can tell that by the charge. An up has a charge of plus 2/3, and that's the most important thing for you to remember, is the charge on the up and down quarks. And the charm and strange and the top and bottom, because again, they go in families. I'll come back to that in a moment. A neutron, on the other hand, is up, down, down. Because you can see, if you've got 1 up and 2 downs, the overall charge of your baryon caused by up, down, down is 0. And it's as simple as that. You just look at what the charges are, and they will add up to whatever the charge of the particle is. Now again, these are effectively small, medium, and large, so most of our matter is made up of up and down. Charm and strange are the sort of medium-sized equivalent of those. And the charm has the same charge as the up, and the strange has the same charge as the down particle. And then the top and bottom are the large versions of our quarks. And again, the charges are the same based on the row that they're in on the table. Now, this seems like a lot of information all at once, so make sure that you pause the video if you need to, sort out what's what in your head. They do form a lovely table when you put them all together, and that is what the standard model is. This is our current standard model. We don't need to know anything about all of this stuff on the right-hand side, so you can just forget about that for the moment and just look. We have 4 rows of 3. The top 2 rows are our quarks, small, medium, large. The bottom 2 rows are our leptons, small, medium, large. One of the things you do need to know, the bottom quark was not discovered until the early 1990s. But physicists knew it existed long before that because they put all of these things in this lovely table and there was a space missing there. They knew there should be a particle that had a charge of -1/3, and they could even predict its mass. They just couldn't find it because their accelerators weren't good enough. Remember, these things are very uncommon matter. Anything that is not up-down electron and electron-neutrino is very uncommon. You need a large amount of energy if you're going to produce in an accelerator a bottom particle because of its very large mass. So it was discovered in the 1990s, and it had the properties that they predicted because of the symmetry of the Standard Model. First and foremost, charge has to be conserved. So anytime there is any kind of decay, any kind of interactions between particles, what goes in terms of charge has to come out on the other side. Otherwise, that interaction is not possible. Our second conservation law is conservation of baryon number. So baryon number, all quarks have a baryon number of 1/3, which means all baryons have a baryon number of 1 because they have 3 quarks in there. All antiquarks are -1/3, so all antibaryons have a baryon number of -1. Whatever number of baryons goes in must come out. So if a particle before has a baryon number of 1, as in there are 3 quarks, what comes out must also have a baryon number of 1. If we look at mesons, we have a quark and an antiquark, so we have a baryon number of 1/3 plus -1/3, overall baryon number of 0. Our next one that must be conserved is lepton number. All electrons and neutrinos have a lepton number of 1. All their antiparticles have a lepton number of -1. And again, what goes in must come out. If you have no leptons going in, you must have no leptons coming out. If you have a lepton going in, you've got to have a lepton coming out. It's that simple. And you just look at any particle equation and you count up how many go in and how many come out, and they've got to be conserved. The next two are sometimes trickier to establish. So mass energy has to be conserved. Well, we know that energy is always conserved. How do you know if energy is conserved, or mass energy in this case? That's difficult to know unless you're given some numbers for mass and energy. There may be situations where you are given the mass of particles that goes in and their kinetic energy, and whatever mass and kinetic energy comes out, they have to add up. That would be a fairly complex question, but it is possible. We also know that momentum always has to be conserved. This means that a particle by itself, for example, if it decays, it must decay into 2 particles going in opposite directions. The final one is a bit weird, and I'm going to try and avoid using the word strange to describe weird, and that is strangeness. Now, with our specification, we don't have to consider the conservation of strangeness, and in fact, sometimes you find interactions where strangeness is not strictly conserved, but our spec allows it. But I think you do need to know about strangeness and its conservation just for your own physics knowledge. So in interactions, strangeness should also be conserved. And weirdly, strange quarks are given a strangeness of -1, and the antiparticle, the anti-strange quark, is given the strangeness of 1. So opposite to our baryon and lepton. That's for your future reference. If you end up doing particle physics sometime in the future, you can conserve strangeness, but for now we don't have to worry about it. Now again, lots of information. Let's look at an example where you actually have to apply these rules. And I've just taken a question from a question paper, and we'll go through the whole thing, including looking at how we figure out baryon structure, mass in gigaelectronvolts per c², and then applying the conservation rules. Okay, so we're told the neutral lambda particle is a baryon of mass that and contains 1 strange quark. We have to try and deduce the quark content of this neutral lambda particle. Some key things here. We know it's neutral, so we know whatever baryons are in there, their charge is going to have to add up to 0. We know that one of them is strange, so it's going to be something strange. And we know that our strange is -1/3. So the other 2 quarks that are in there are going to have to add up to +1/3 in order to end up with a neutral particle overall. And so we look at our table and we figure out what combination of 2 baryons that are not strange, because we know it only has one strange quark, is going to give us a charge of plus 1/3. And clearly, that's one up and one down. The up is plus 2/3, the down is minus 1/3. Our 2 minus 1/3 are going to balance out our plus 2/3, giving us a neutral particle overall. So you see, there's no great mystery to it. It's just being a little logical about it and spotting the clues that they give you in the question. Calculate the mass of the neutral lambda particle in kilograms. They told us that the mass was 1116 megaelectronvolts per c squared. And again, this is a very common question. It comes up all the time. You can see it's worth 3 marks. This is very straightforward if you know what you're doing. So we know 1116 megaelectronvolts is the energy equivalent of this mass. That's the way to think about it. So 1116 times 1.6 times 10 to the minus 13, because it's mega electron volts and not electron volts, is going to give us the energy equivalent of this mass in joules. We know that that is going to be equal to mc squared. If you do this sum, you get 1.7856 times 10 to the minus 10 is equal to mc squared, and then you just go ahead and divide by c squared, and you end up with an m of 1.984 times 10 to the minus 27 kilograms. The key here is to remember, when they give you the mass in megaelectron volts per c squared, you just think of that as that's the mega electron volt energy, and I'm just turning that into joules and then using my equation. This is a really nice question, and it really tests your particle interaction and is the perfect example of applying our conservation rules. So it says, here are 5 possible ways suggested by a student that our lambda particle might decay. And these are, deduce which of these decays are not possible. So what I'm going to do is I'm going to do the first decay in some detail, go through each of the conservation laws, and then we'll be able to apply those conservation laws a bit quicker as we go down through each decay. So let's look at the first one. They're suggesting a lambda particle decays into a proton. They haven't put the plus, but we can put the plus in. And a pion. Now you need to know at this point that a pion is a meson, and therefore is made up of a quark and an antiquark. Alright, we start with charge, because that's the easiest one. We've got neutral, we've got plus, we've got minus, so in terms of charge, we're all good. Our next one is baryon number. Now we know that our lambda particle is a baryon, so it has 3 quarks. We've already established it's up-down strange, which means it has a baryon number of 1. We know a proton is up-up-down, because that's something we need to know, and therefore has a baryon number of 1. We know that a meson is a quark and an antiquark, and therefore it has a baryon number of plus 1/3 and minus 1/3, giving it a total baryon number of 0. So we have 1 on the left and 1 on the right, and our baryons are conserved. Our next one is leptons. We have no leptons on the left, and we have no leptons on the right. So in terms of leptons, we have 0 and 0, so that's conserved. Momentum. Well, we know that our lambda is decaying into 2 particles. Feasibly, those 2 particles could go in opposite directions, meaning there's no reason to suppose that our momentum is not conserved, and we don't have any information on mass energy, so that we couldn't possibly establish whether or not mass energy is or is not conserved. So we're going to go ahead and say the first interaction is possible. Let's now look at number 2. In terms of charge, this is good, because we've got plus and minus on the right and we had neutral on the left, so charge is conserved. What about our baryon numbers? We had a baryon number of 1 on the right, and we have 2 leptons over here which don't have a baryon number at all. So our baryon number is not conserved, and therefore interaction 2 is not possible. Number 3. Alright, charge is good, because we've got our neutral particle on the left, a neutron, and a neutral pion on the right, so charge is conserved. What about baryon number? We know we have a baryon number of 1 there. A neutron is up, down, down. 3 quarks, therefore a baryon number of 1 as well. And we know that our meson has a baryon number of 0. We've established that earlier on. So our baryon number is conserved. It's all good. Lepton number, conserved with no leptons left or right, so it's 0, 0 again. And again, our momentum is potentially conserved because our single particle decays into 2 particle, which could go into opposite directions. So we're going to go ahead and say interaction 3 is possible. We have no information on mass energy. 4. In this case, our charge is good. We have our neutral lambda particle and a neutron, which we know has a neutral charge. Charge is conserved. Baryon number will be conserved because we've got a baryon number of 1 on the left and a baryon number of 1 on the right. Lepton number is still 0, 0, all good. Momentum here, however, is not conserved because you cannot have a single particle, whether it's still or moving in any particular plane, decay into another single particle. So number 4 is out as well. Number 5, let's have a look at this. Our neutral lambda changes into a proton plus a neutral pion, and we can see straight away that charge is not going to be conserved here because we've got 0 on the right and we've got +1 on the left, and therefore that one is not possible either. Like I said, this is the perfect example, displaying what you must do to any random interaction to see is it a possible interaction or not. And none of it makes sense to the uninitiated. None of these symbols, none of the baryon number, the lepton number, all of that stuff, until you get used to doing it. So get some questions, do some practice, get used to figuring out what the baryon number, lepton number, etc. are, and make sure that you can figure out these interactions.